Log on, tune in, find out. Another good idea from Cambridge.
And associated with this matrix, I will define a monoidal category. So that monoidal category builds on the Hacker algebras I defined yesterday, but so I will give a direct presentation of that category. And if you remember yesterday's definitions, I defined a very general family of algebras depending on a matrix, Hermitian matrix of polynomials. And then I said if you start with a Cartan matrix, you should look at polynomials with bounded degree, with some fixed bounded degree, depending on the entries of the Cartan matrix. And then you take the most generic polynomials, so that means you're going to work over a ring with many indeterminates. And so I would like to take this setting here. So it's going to be a monoidal category over some commutative ring, which is I call K, double bar. So it's a commutative ring with indeterminates Tij and Tij or S, where R and J are distinct and they have an indexing set I, and R and S are between 0 and Mij. So this Tijrs is an indeterminate and it's defined under those conditions. And there are symmetry properties required, which I won't recall, which is Tijrs is the same as Tjisr, and Tij is Tji when Mij is 0. Okay, anyway, so there's this big coefficient ring. And this monoidal category is given by generator and relations. So the generators, so I will first talk about objects. So the generating objects are EIs, with I in I. So that's it for objects. So usually there isn't much going on with objects in a category, in a monoidal category. There's more going on with arrows. So that's all I'm going to say about objects. So what that means is that the objects of that category are exactly a tensor product of EIs, or products of EIs. So maybe I should have made it clear that when I talk of a monoidal category over K, I really mean that it's a linear category. So when I talk of generators, I also include that additive structure, which means the objects in my category are going to be sums of products of EIs. So it's, maybe I can put it here, objects of B, or B of A, or sums, palette sums of products of EIs. So it's not, the objects are quite easy to describe. So now I want to put maps between the objects. And so the generating arrows are of two types. First type is xi, which is going to be an endomorphism of ei. And the second type is tau ij. It goes from eij to ej. So that's it for the generators of the category. So that means in this category, so the objects, it's fairly easy to say what they are, but the arrows now is very complicated. Get something very complicated because you can compose arrows in two ways in a modular categories. You can take compositions, so you can look at things like xi square going from this object to itself. You can apply tau ij, and then on this object you have various endomorphisms. You can apply xj on the first factor, xi on the second factor. You can multiply all these things together, and so you get a very, very big category. So there are way too many arrows, and so we're going to put relations. Again, the relations involve only arrows, and they don't involve objects. So the relations are going to be reminiscent of those I described yesterday for Hacker algebras. So the first relation involves tau ij square. So if you do tau ji composed with tau ij, that's an endomorphism of ei ej, and as such, it's given by the following formula. Now I need to explain what I mean by this notation here. So that is an endomorphism of the object ei ej. Ei times xj denotes the endomorphism of that object. That is, you do nothing here, you do the identity here, and you multiply by xj on ej. And similarly here. And now we take a polynomial in those two variables. So that defines an endomorphism of this object ei ej. And so I probably should recall that qij is a polynomial in two variables, which involves those indeterminates, and it's tij u to the mij plus tji v to the mij plus a sum of tij rs u to the r v to the s. At least when mij is non-zero. So that's the first relation. The second type of relations involves commuting a tau and an x. So let me. So now this equality takes place in the space of maps from eij to eji. So what you can do is first apply x here, then apply tau. And compare that with applying first tau, and then applying x on the ei. And the difference is, well, 0 or 1, which means the identity of the object when I equals j. So when I equals j, you have same object on the right and the left, ei square. So ei ej means ei tensor j, if you want to think with a tensor product in your modular category, or you can just write product like this. Okay, and there is a similar relation where you switch left and right. So that's tau ij composed with ei xj minus xj ei. Tau ij is minus delta ij. And there is a final relation, which is a braid relation. And it says the following. So I should say, so the last relation is going to, I have to explain, it's going to be taking place in homomorphisms from ei ej, ek to ek, ej, ei. So I'm writing that to so that you have a better idea of what I'm writing. So there are two maps going from this product to that product. You can first switch these two terms using tau, then those two, and then these two, and you get there, or you can start swapping there. Okay, so that means in a formula, you do tau ij, and then on that term, and then you do the identity here, which I write as ek. Okay, so that's a map from this triple product to the triple product where I have switched ej and ei. I do my morphism tau here and the identity on ek. Then the next term is going to be ej tau ik, and the final rightmost term is going to be tau jk multiplied by ei. So if you do, and now if you do the, if you go from here to here the other way, then you, what is it you do? Ei tau jk tau ik ej and ek tau ij. So these are the two ways to go from one to the other. And this difference is usually 0, but not always. And when it's not 0, it's a case where those two objects are the same. So something funny happens only when these two objects coincide. That is when I equals k. And in that case, you get xi. So you multiply by x here, or you multiply by x on the second term. So let's say it's going to be the case where I equals k. So I'll write I in place of k there. Ei, ej. And then we have a polynomial q ij of xi ej ei xj times ek. So, sorry, I decided to call that ei. So you can do endomorphisms of this object here by applying powers of x here and powers of xi here, powers of xj there. Or you can do something similar by working on the second and third term. Oh yeah, it's eij of ej xi xj ei. And as yesterday, this polynomial is divisible by that polynomial. So this actually is a polynomial in the xi and xj's. And this is 0 if I is not equal to k. So that's the definition of this monoidal category. So it's relatively short. And it's actually a compact way also to describe the Hecker algebras of yesterday. So let me say that first. So if you take n an integer, you can look at the endomorphism ring of the sum of all products in U1 in UN, where nu is in I to the n. So that's a big algebra. My claim is that there is an isomorphism with the algebra Hn associated to this A. So the algebra from yesterday. And that's defined as follows. Well, one nu is mapped to the projection on the new term. X A nu. So it's something that's going to happen only on the mu term. And on the mu term, we are going to apply x, a certain x at the position A, starting from the right. So and this is right. Okay, I'm sorry. I should have parameterized things like this. That's a bit. It's going to make the next formula a little bit easier if I write things like that. So that's E nu n E nu a plus 1 x nu a E nu a minus 1 E nu 1. So what does that mean? That means x and u is 0 on all those objects except precisely for nu. And for nu, it's a certain endomorphism of that object. So you do the identity on all terms except at position A, where you apply the corresponding x. Okay, so that's an endomorphism of that product here. And for tau, we do something similar. We map that onto say E nu n E nu a plus 2. Then we do tau. And then we do so yesterday's Hacker algebras occur as endomorphism rings of objects in the category B. So one thing that's clear from the definition is that if you take products of E's and the number of terms, you take two products with different number of terms, there are no maps between them, okay? Because the way I've defined x and tau, they preserve the number of terms. So there's no point looking at terms between two products like that, one from an n and an n prime, which are distinct. So that gives you these algebras, the Hn of A, they describe exactly the homomorphisms in the category. And these idempotents here, they have a very clear meaning here. They involve looking only at one specific product of E's.
In your definition of the category, in this I equals k case, there's an inverse of a morphism.
Yes. Yes.
How do you know that's invertible?
So it's just a shorthand because this, you see, I have a polynomial here, and the first term, no, what is it? The second, I'm evaluating this polynomial qij. It's a polynomial in two variables, but the second variable here and here, some of them are the same. So what I have here and here is a certain polynomial evaluated at xi ej ei, and the same polynomial evaluated at ei ej xi. So it's a usual fact that if you take a polynomial evaluated in A minus polynomial evaluated at B, is divisible by A minus B. It's just the notations are categorical notations make that a little bit obscure. But that's, okay, maybe I can take, I can write that down. You can write P of A as Qij of, now I can write things in a slightly different way. A, comma, Ei xj Ei. And then what I have here, if you take A equals, sorry, yeah, if you take the formula I have here is xi ei ej, ej minus ei So that's a way to rewrite what I have written here can be rewritten like this. And now it's a certain polynomial evaluated at that variable minus evaluation at another place, and that's indeed divisible by this. It's all everything commutes because when you take a product of objects in a monoidal category, if you take an endomorphism of the first object, an endomorphism of the next object, these two commute, the basic axiom of monoidal categories. So these two endomorphism of my triple product do commute. So that's all happening in a commutative world. So I could write that as a more complicated polynomial. I could do an extension. I don't know if that completely, but it's a note. I mean, the notations are I mean, I try to make them as compact as possible. I could write a more complicated sum, but it is divisible. And if you look at the statement here, it's some of that. Your question is boils down to the same question about yesterday's algebras, except that in the language I used yesterday, non-categorical language, it was maybe clearer that there was the divisibility property did hold. So that is a polynomial in xi, ei, ej, ei. Okay, so we have a monoidal category, and its objects are products of E's. And so the idea is that it should look like the positive part of the enveloping algebra of Kac-Moody algebra of that type, or you can think of a complex semi-simple algebra. It's not much difference with the general case. And so it's defined over Z. So enveloping algebras over Z, they are not quite generated by EIs. You have also to add divided powers. Okay, so that's the usual Z form of the enveloping algebra. It's positive part. So how do you define divided powers? So you take EI, you take the nth power of EI, so that makes sense. You take the tensor product of your object n times. How do you divide by n factorial? So that's something that Joe explained in the case of SL2 last week. And the same recipe works in this framework. So let me explain divided powers. So the problem is what is EI to the n. So to divide a space, to divide the dimension of a space by n factorial, one way to do that would be to have an action, a free action of the symmetry group Sn, and then you would take fixed points. So if you have a vector space, free representation of the symmetry group, you divide its dimension by n factorial like that. So here there is no symmetry group around, but there are Hecker algebras, and they are good enough, so even better than the symmetry group. You'll see why in a minute. So what kind of Hecker algebras are acting on EI to the n? Well, if you look at what's happening here, if you consider only one I at a time, you will be really looking at the Hecker algebra Hn associated to a matrix, a 1-by-1 matrix. So there is a map, the claim, that if you restrict the morphism above, you get a map from Hn of this set I to the endomorphism ring of EI to the n, and that's I explained yesterday. That's the zero Hecker algebra. That's we'll call it maybe by 0 Hn. This is a affine Hecker algebra. As an algebra, it splits as a direct sum, as a tensor product. As a vector space, it splits as a tensor product. So I need to say a few words about that. So we consider only one, a set with only one element. So all these complicated things, there is only an xi, there's just one xi, and the tau ij's are really tau i's, but I can put them in different positions. So I can consider the xa, and the nu is constant, so the xa and tau a's, and these are, so the xa's here, and the tau a's are going to generate this subalgebra. So this is a subalgebra generated by tau 1 up to tau 1 minus 1, and that's 0. That's the nil Hecker algebra. So that's, well, I can put the relations here. You put the usual Hecker relations, but tau I square is 0. Because my polynomial q, when I equals j, is equal to 0 by definition. So that's the nil Hecker algebra. It has a basis. Sorry, no, I don't need the basis here. Do I? Yeah, probably I need the basis now. So it has a basis parameterized by elements of the symmetry group. So if you take W in the symmetry group Sn, and if you take W equals S1, Si1, SR1, SRD, a reduced decomposition. So here S indexed, an integer is a transposition, that integer and that integer plus 1, the usual thing. So then you can define tau W to be the product tau R1, tau RD. And this is independent of the decomposition. That's the usual Hecker thing. And the set of tau W gives a basis. That's, these algebras are classical Hecker algebras, specialized. So you can't say the usual algebra depending on the parameter q. You have to take two parameters. Instead of -1 and q, you take 0 and 0. So you have this relation, usual basis. And you tensor by a polynomial ring. So you affinize that algebra. And now I want to define an element. So these algebras are very easy to deal with, extremely easy. They are actually Morita equivalent to just polynomial rings. So it's when you see these algebras, all these things are classical facts that are places in the literature. So and the best way to see it is to define an idempotent Bn to be Tw0 times x1 with the n-1, x2. Okay, I use small x's. I should stick to that. W0 is the longest element. And that's not a t, that's a tau. Okay, so I take the product, I take the longest element in the symmetry group, I take the corresponding product of taus, and then I multiply by polynomials, and this is an idempotent, Bn squares to itself. And I mean, it's very nice. It defines what do I want to say? Yeah, there is a Morita equivalence. And one way to say it is that there is an isomorphism. So if you truncate your algebra by this idempotent Bn, this is isomorphic, you get your algebra back. So there is an isomorphism like that given just by multiplication. So this here is a bimodule for the left action of invariant polynomials and the right action of the algebra itself. And the claim here really says that there is in other terms, what that means is that Bn0Hn gives a Morita equivalence from between the invariant polynomials and this algebra, this nil affine Heiko-algebra. So the nil affine Heiko-algebra is the same representation theory as invariant polynomials, symmetric polynomials, and actually it's a matrix algebra. I mean, it's one of those cases where, anyway, this is a polynomial ring, and anyway, your projective module there is free. So you're realizing this nil affine Heiko-algebra as a n factorial by n factorial matrix algebra over invariant polynomials. And that's expressed by this isomorphism, which is what I will use now. So this is elementary. I mean, all these statements are quite elementary to check. No fact that Bn is an idempotent is a classical fact in terms of Schubert calculus. You should think of the taui's as divided difference operators. And if you take this element x1 to the n minus 1, etc., and you apply these operators, you go down to, you generate polynomials over symmetric polynomials, etc. The usual Schubert calculus story for a symmetric group. Okay, so now the idea is that multiplying by Bn on any module for the nil affine Heiko-algebra is going to divide the dimension by n factorial. So it's quite clear. If you look at this bimodule, so let's say if you take M and is a module for this algebra, then the rank okay, I should say that Bn times M, if you take n factorial copy of that, this is isomorphic to M, at least as vector spaces. You see, because to get M back, you need to go from invariant polynomials to polynomials, and polynomials is a module of rank n factorial over symmetric polynomials. So that means that if we take a module for this nil affine Heiko-algebra, we can divide its dimension by n factorial just by multiplying by Bn. So now we can come to a definition of the divided power. So now we define the divided power of this functor. Well, on this object, sorry, the object ei to the n is acted on by the nil affine Heiko-algebra, and so we can multiply by this idempotent. So when you have an additive category, when you have an abelian category and an idempotent in the homomorphism ring of an object, you can take the image of the idempotent, you get a direct summand of your object. That's what I'm doing here. Well, the trouble is that my category is not abelian. I just took a linear category. So I can take direct sums of objects, but I can not take kernels, co-kernels, images, etc. And I cannot even take direct summands. Well, I might as well change my category to allow for that. So that's an object in a new, slightly bigger category, B upper I. So B upper I is the idempotent completion of B. So B is a subcategory, a full subcategory of B upper I. That's a full subcategory. And the objects of this category are exactly finite direct sums of direct summands of objects of B. Or in other terms, objects of Vi are direct summands. So you can make a category like that. There's a formal construction. You can think of that as some kind of universal two-categorical problem. You have to represent certain two functors, and this is represented by this category. So you switch from the world of k-linear categories to the world of k-linear categories such that idempotent splits. So formally, you can get a new category where now every object, whenever you have an object, if you take an idempotent in the endomorphism ring, then you can consider the corresponding direct summand of the object. Okay, it's sometimes called Karoubianization, and it's sometimes called pseudo-Abelian closure, which is probably a very bad terminology. So I think idempotent completion is more reasonable.
Right. So you're taking the closure in for divided powers of EI and EJ and all of these?
So this category has nothing to do with EI. It's a general construction. When you have an additive category, you can construct a new category. So, the I here, okay.
Oh, okay.
Idempotent, I should,
okay.
yeah. Thanks. Yeah. And so far, I hasn't been a square root of -1 yet, but it might come at some point. So we have now a slightly bigger category, and the claim is that it does model the positive part of the enveloping algebra of Kac-Moody algebra. So I should tell you a few things about Kac-Moody algebras. Associated with A. So what you do is that you take the free algebra, that's a free algebra generated by elements EI, FI, and HI for I in I with relations. So the relations are the HI's commute. So the commutator of an HI and an HJ is 0. The commutator of EI and HJ is AIJ EI. Commutator of FI AJ, so it's the usual relations. It's minus AIJ Fi, and I need the interchange between EIs and FJs, and the easiest way is to say that if you add EI and you raise that to the power 1 minus AIJ, and you apply that to EJ, this is 0, and same for with Fi. And here add is an operator. Add x applied to y is the commutator xy. It's a compact way to write the Serre relations. Thanks. Checking the notes. So last relation is that EI and FJ tend to commute. Right, so that's an algebra. Let's say we take the Q algebra. And inside that Q algebra, we take a lattice. So Chevalet, whatever, Chevalet, Constant, Cartier, whatever lattice. makes representations of nice definition over Z. So UZ is a subalgebra generated by divided powers. So EI to the n is by definition EI to the n divided by n factorial, Fi to the n, and Hi's. So it's a Z subalgebra. So that's the algebra. That's the Z algebra that you use for when you look at, say, representations, characteristic P or you reduce mod P. And inside, you can consider the positive part. Still about Z subalgebra generated by the EINs. So that is defined. I mean, you could give a direct definition by generator relations of that Z algebra. That involves, I mean, you only need one type of relation. And the claim is that these relations hold in the category, category B. The category B, in that sense, categorifies this algebra. We have space here, proposition. So if you take I and j in I, say I different from j in I, and if you take what this relation says can be expressed in a slightly different way. So if you take commutators that involve signs, saying, for example, that the commutator of an element x and an element y is 0, so that's xy minus yx is equal to 0. If you think of objects in a category, like B, you can take products, but you cannot take difference. You can take only sums of objects. But you can, of course, rewrite xy minus yx equals 0. It's xy equals yx, and in the category, it should really mean xy is isomorphic to yx. And so you can, when you have this complicated identity, it does involve signs, but you can put all plus terms in one side and move the ones with the negative sign in the other term, and you get the following.
Didn't you say your category was over this commutative ring?
So the morphisms are over the commutative ring. The morphisms are k modules, but the objects themselves in a category, you cannot multiply an object by a scalar. So that's the scalars are only at the level of Hom space, and here I'm giving a statement which is about the object. So you can just have this kind of semi-group structure on the object. You can multiply and add objects. So semi-ring structure. So if you take the sum over, say, R even, run over even integers, and you take EI to the M minus R plus 1, so I will put n equals mij, which I define as minus aij. Then you take ej, then ei. It's the same as the sum over R odd. That's to the power R of ei to the, so that's the same thing, m minus R plus 1, ej. So this is an equality that involves finite direct sums, because I mean this becomes negative, and so consider that to be 0 when R is large enough. So that involves finite direct sums of objects of the category B, or rather it's idempotent completion. And the two objects, are isomorphic, and there is a canonical map realizing this isomorphism. And this relation is really the relation, this add relation there. So in other terms, what this says is that there is a morphism. There exists an algebra morphism from this U plus Z to the Grothendieck group of this category BI, which sends EI to the n to the class of EI to the n. And the Grothendieck group here, the Grothendieck group of an additive category, the special case of the Grothendieck group of an exact category. And probably you might know the abelian case. So here, case 0 is a free abelian group over isomorphism classes of objects of that category modulo the relation that class of M is class of M1 plus class of M2 if M is isomorphic to M1 plus M2. That's a very so-called, sometimes called split Grothendieck group. There is no notion of sub-objects or quotient objects, and the only notion of exact sequence that makes sense is the notion of split exact sequences. So you use that to define a Grothendieck group. So statement is that the in this category B, if you forget about maps, you look just at objects up to isomorphism. What you get is come from this enveloping algebra UZ+. So when there are obvious questions like, is this map have check relation, defining relations? Defining relations here do hold there. And you can ask if the map is surjective or injective, and it is both surjective. It is an isomorphism. But that, no, it's not. I mean, in this case, I can't show it, so it should be an isomorphism. And it can be proved not over K, but over a certain specialization using geometrical methods. But it should be possible with, by studying the representation theory of those algebras, of the Hecke algebras, it should be possible to, it shouldn't be too difficult to prove that this map is an isomorphism, but it's not completely, it's not trivial. So I'll talk briefly about specializations. So if you specialize okay, let me first say that if you assume that A comes from an oriented quiver, so that means the set I, you start with a graph with the vertex set, the set I, and you put Mij edges between I and j when I is not equal to j. So you have a graph, and now you choose an orientation of the graph. Then that gives you a specialization of that ring K. And so you can define a new monoidal category, B, Z, as a tensor product of this big monoidal category. And you can do the same. You can also take the idempotent completion. There. Right. And so you can reduce the map there. And so there is a reason for specializing. There's a reason for not studying the general ring K, but putting some extra, specializing certain parameters. It's to get a grading. So I explained that the Hecke algebras, yesterday's Hecke algebras, didn't have an obvious grading because the polynomial Q are not homogeneous as polynomials of two variables. But if you choose this specialization of the polynomial Qs, they become homogeneous polynomials. So that category can be graded. Can be graded by putting. So a graded category in that sense means that the maps are given a certain degree. So you put x's in degree 2, and you put tau's in degree mij, degree aij, I'm sorry. So when you have a category where the maps are graded and the composition, all the structure is compatible with the grading, well, it's actually the same data as to be given a graded category in the traditional sense. That is a category where you can shift objects. Okay, so a category with a translation functor. And so maps, I should say, maps can be graded. And you can define an associated graded category. There's an associated graded category, which we can denote with a dot. So you can put a bullet there to say it's graded. And same, you can also take the idempotent completion, etc. So you can define tons of categories, and I'm only telling you about maybe half of them, but already more than you want to hear. So these categories are the fact that you have a grading, that you can shift objects, whereas here you have only graded HOMs. You can think of the category of vector spaces. So if you look at the category of graded vector spaces, that's a category where the objects are, they are graded vector spaces, and the maps are homomorphisms that preserve the grading. So that's really a graded category. You can shift your vector spaces. It's an ordinary category together with an autoequivalence that shifts the object. On the other hand, when you have this category where the objects are graded vector spaces, you can change the homomorphisms in your category and decide that HOM between two graded vector space is HOM as a space of linear maps, ungraded. Okay? But now the space of homomorphisms acquires the structure itself of a graded vector space. Two graded vector spaces, you look at maps of not necessarily homogeneous, that's a graded vector space. So you can think on one hand of a category where the maps are graded vector spaces, or you can think of a category where the maps are ordinary vector spaces, but you can shift the object. You can think in two ways of the category of graded vector spaces. And so these are equivalent notions. And here I'm passing from one to the other. Okay, so you can think or ask me later about this, but it's just an easy categorical fact. Just there are two categories that are equivalent there. Okay, so there's an associated graded category, and of course, when you have a graded category, there's going to be a parameter Q, the Grothendieck group here. Okay, so you have to split idempotence, and then it takes this graded category. So that becomes a module over the ring of Laurent polynomials, where so graded category means you can shift your object. So if you take an object and you shift it, you decide that its class, I should call that a V, is V times the class of M. So this automorphism of your category, you call it multiplication by V on the Grothendieck group, and that Grothendieck group, the Grothendieck group of an additive category is an abelian group. The Grothendieck group of a graded category becomes a module over that ring. It's also an algebra because it's a modular category. So at the end, we have an algebra over that ring. When you specialize V to 1, so you forget about that automorphism, you get the Grothendieck group of the ungraded category. So what you expect should expect there you get a deformation of that algebra, and that's indeed the quantum group. And that's just checking that the isomorphism there is provided by a map that respect gradings in some sense. So it just checks that whatever should be true is true. Just have to compute degrees. And so a proposition say is that there is an algebra map from what I would call UVZ plus say or U ZV the inverse to K0 of that category here. So we have a category defined over the integers. We split idempotence, and then we view it as a graded category. And that's a quantum group. That's a positive part. Of quantum group in its integral form defined by Lustig. So you take Q divided powers of the EIs that defines the lattice inside your quantum enveloping algebra. So there's an algebra map. And in that case, where you work over Z, that is, you have specialized your polynomial from general K to Z, one can actually show that this map is an isomorphism. So I'll explain that in the last lecture using geometry. So what I should say at that point is that these constructions have been carried in a slightly different setting, bit restricted, and for different specialization, they have been carried also by Kovanov and Lauda. So this result here is valid for that category B. You don't have to specialize. You can work with K. You can take any specialization, and you will still get a morphism like that. So Kovanov and Lauda, they study a category, and Hecker algebras associated to other polynomials Q, and that statement remains true. So they have also proved this theorem, this proposition, and it's graded analog. But we'll see in the last lecture that this different specialization here is the one that relates to the geometry, and for that specialization, so not only is this map an isomorphism, but the canonical basis here becomes a basis here that has representation theoretic meaning. Namely, if you look at your category where you have either direct summands of objects, you can ask what are the classes of the indecomposable objects in the category. At least here I have a category defined over Z. You can extend scalars to C, to complex numbers. So you have a nice category. And you can ask what are the classes in the K0 of indecomposable objects. So that's really about indecomposable projective modules for the Hecker algebras I introduced yesterday. So what are their classes in K0? And as you would expect, I mean, they do correspond to the canonical basis. So that's a consequence of Lustig's geometrical construction of the canonical basis here, and the geometrical realization of that category. So that map will be shown to be an isomorphism, and canonical basis here corresponds to basis of indecomposable object. Right, I think that's probably for today. So I should say a few words about what I will be doing next. So the difficulty of going from the positive part to the whole enveloping algebra is in this categorical framework is the same as in the, to some extent, is the same as in the algebraic framework. So if you know half, you have been able to construct that algebra. How do you define the big algebra? Well, there's a nice way, which is to, of course, you have to add HI, but forget about that. You have to take the positive half of your quantum group or your enveloping algebra, the negative half. The more you pair them together, and that defines the whole, that defines the big algebra. So you don't really have to worry too much about this relation, about the relation. So you can. What's important is that in some sense, the EIs and the FIs are forced to be dual objects in your algebra. At least in the in this case it's symmetric. Kac-Moody, it's correct. So tomorrow we are going to take this approach to say, well, we have constructed half. We'll formally add some kind of dual half to our category B. It's going to be much bigger, and so each object EI is going to have some dual FI. That's going to give a very big category, and we still need to factor out some kind of radical or to add some relations. And this is some of the subtle points in the construction, and that's, the critical thing that we have to do has to do with this relation when I equals j, and that's something of SL2 type. We want to see the relations that the commutator of EI and FI is an HI, and so that boils down to SL2, and that's then you can apply some of the techniques that Joe Zhuang explained last week. So from there to do the general, to get the general category, we'll need to bring back some things about SL2. Okay, so that's all for today.
Any questions?
So there's an additional relation, I guess, in the U plus Z, which basically says what happens when you take EI to the N, EI to the M, and EI to the N plus M. Does that correspond to something with the BNs?
Yes. So it's something that's that says, what does it say? It says if you transform in terms of Morita equivalences, it's fairly banal. But basically, you want to compare Bn with you write n as I plus n minus I. You want to compare it with Bi times Bn minus I, and it's the fact that. Something like if you take invariant under Sn minus I times Si, it's a free module over a certain rank, so it's this kind of statement that gives that relation. So it does hold because it holds for polynomial. Okay, yeah, so
So by defining your category, your monoidal category abstractly, like you get a really general theory, can you construct some sort of concrete category using the Cartan matrix that satisfies the relations, or is it we do it abstractly?
The only way to define the category in a different way is to use the geometry of Lustig quiver varieties. So I don't know of another way, and that only defines this only takes care of that specialized category. But it's okay that there is this more general category, more general default category. I don't know if there is another construction, but I don't know a direct construction that wouldn't be by generator relations in some sense. Yeah.
You can also recover full algebra structure music cost.
Okay, so I'll mention that in the tomorrow or in the fourth lecture. So this is, for me, that's a point about doing all this work is trying to. What about the half algebra structure there or there? So if you look at quantum groups, the half algebra structure in quantum groups you have this R matrix, etc. And at the end, this half algebra structure gives you invariance of three-dimensional manifolds, the half algebra structure on quantum groups. So the reason for developing all of that, probably the main reason, is that you can indeed define some kind of hop structure on that category B. It is possible. But it's not something going from B to B tensor B. It's some kind of homotopical version of that. So you need so you can define some kind of there is some kind of coproduct, but you have to pass to categories don't work. You have to pass to suitable infinity categories and do suitable simplicial constructions, and then you can construct something like that. Yeah. So I won't discuss this construction at all, but this is the main one of the main reasons to do this deal with these categories.
Is it easy to say what the morphism is that induces the Serre relation?
No, so originally I proved this relation abstractly, and Kovalov and Loda they wrote down an isomorphism, so I thought, oh yeah, that's much better. That's much better. And their isomorphism is indeed quite concrete. It's not a good idea to think too much of that, but you have to think of some kind of zigzag. So you start at r equals 0, you have a term, and then the term r equals 1, r equals 2, and you will have maps going like that. Okay? So direct sum here is isomorphic to the direct sum there. And there are maps actually going both directions. There's an isomorphism this way and the inverse that way. And so you should think of going one way as a complex. And that complex is actually homotopy equivalent to 0. And the maps going this way are splitting homotopies. So that's the nice what happens. And at the end, of course, you deduce that. And these maps, they are explicit maps. You use, again, idempotence. You write down explicit things. So it's fairly short, but it's, yeah, I mean, it's better than to try to prove something abstract, which you can actually prove only by having first develop some representation theory. So there's explicit proof. But I could write the formulas for the maps this afternoon. But the idea is to think of a complex that is not just zero cohomology, but that has that's a split homotopy account.
So no questions. So let's thank the speaker again.